conditional probability, likelihood ratios, and the C statistic. Now, does that sound interesting or what? So for those of you who are hoping for information that will be in a multiple choice test on your boards, you might as well just take a nap, because you're not going to get any of that. What you're going to get is an understanding of how we use the rules of probability to make sense of data. And first, we're going to cover that from the perspective of understanding how we can use a diagnostic test to change our opinion about the likelihood of disease. It's a very upsetting topic. A lot of people get upset about this. It's very controversial, and if you're a Republican, you might as well just leave right now. But then we're going to talk about the C statistic, and what does C stand for? C statistic. Cool statistic, that's it. So let's go on. Why dice, other than they're pretty and they were in 3 colors? Because although statistics can't tell us the truth, statistics gives us a framework of talking about our experience according to rules, and the rules are derived from probability distributions that reflect the play of chance when there are multiple factors involved. So those who believe in mechanistic thinking often get frustrated with statistics because statistics always ask, how does this differ from a probability distribution where chance plays a role? But, and I can understand the frustration. Statistics can never tell us what is true. You can run anything through statistics. Statistics keeps us honest and makes us argue according to rules that we can all agree on. So, having said that, let's go to a common problem. So we can all participate on a voluntary basis, and Philip is going to be the first volunteer.
So 67 goes email text today. Hypertension, hyperlipidemia.
Yeah, hyperlipidemia.
Not yet tobacco. Left 2 months. She has sharp left frontal chest pain. Mostly happens to climb stairs, but also goes to bed. It's gone for like a few minutes and might get better with time.
Or it might not.
I mean, not.
So what do you think? What is the probability that Mary has obstructive coronary disease? So we're not going to play with microvascular angina, and we're not going to play with this or that, or endothelial dysfunction. What is the chance that we take her to the cath lab and she has a 50% stenosis, a 70% stenosis, a stenosis with an FFR of 0.75?
So
whichever of those criteria you want to use as truth. And so intermediate means 50-50.
Yeah.
Okay. All right. So let's keep that in mind. And I interrupted. You were going to give a rationale.
No, it's fine. Because of her age, she gets some points in diabetes, and then the chest pain is atypical.
Yeah. So we would summarize this as age, 3 risk factors, atypical pain. So, but we want to make our reasoning more explicit. And we want to try to conform. You could tell I couldn't figure out the, whoa, back, you bastard. Okay. I couldn't figure out how to get the line to show up underneath. And the fellow wasn't very helpful. Where's Jeremy? Jeremy was not very helpful with this morning. So how do we picture the question? in terms of probability. And I thought that this Venn diagram is a good way to introduce this question, the question of how to deal with multiple probabilities. She has 3 risk factors, she has atypical symptoms, she's 57. Given that, what is the likelihood of heart disease? So this is how John Venn, that was Venn's first name, would have conceptualized this. He would have said that there's a population of all women. I could have made it all women, but I made it of all 57-year-old women. And then there are 2 subgroups. There's the group of women with coronary disease, and then there's a group of women with atypical pain and 3 risk factors, and they overlap. And in that overlap, we get a smaller group that have coronary disease. So not every woman with 3 risk factors and atypical chest pain has coronary artery disease. So instead of obstructive, I'm just going to say coronary artery disease. And there are some women with no risk factors who will have coronary disease. And, you know, I haven't drawn this in proportion, have I? Because this circle would have more women with coronary disease than this circle, and I haven't portrayed that accurately. But if I did draw them in proportion, then you could imagine that the area subsumed by these different divisions would correspond to the proportion of women affected. So the other way to think of this, and this may seem painfully obvious, is that we have smaller and smaller subgroups as we further divide this information. Now, how do we make the transition to calculations? So if we said that if we want to know the probability that Mary is a 57-year-old woman and Mary is a woman with 3 risk factors and atypical chest pain, given those facts, what is the probability of disease? We would express it as that what is the probability that she has 3 risk factors, plus what is the probability that if she has 3 risk factors, she has heart disease, the probability that she has atypical chest pain and heart disease, minus the probability that she has both chest pain and coronary disease. So that got a little muffled. So if the probability that Mary has 3 risk factors and atypical chest pain will be equal to, that's this, so 3 risk factors and atypical chest pain is equal to the probability that she has 3 risk factors and the probability that she has atypical chest pain. Did I go the wrong way? Minus the probability that she has both 3 risk factors and atypical chest pain. So we can solve that equation for the question, the goal of this is that if she has A and B, if you remember the Venn diagram, that was coronary artery disease. So the beauty of this is that we can solve for having coronary artery disease, given the probability, the other probabilities that we have. So we can reestablish it this way. We can rephrase it this way: the probability that she has coronary disease, given the probability that she has 3 risk factors and atypical chest pain, is the probability that she has coronary disease divided by the probability that she has 3 risk factors and atypical chest pain. Go ahead. No, it's not. There is no causation. So we say this is an observation. So we bring causation with our theories to this.
That's what we discussed. Does this probability explain the recovery from this chip?
They are related to each other, but in this case, the relationship is only mathematical. So if I observe that this proportion of people with atypical chest pain have coronary disease, then that is the probability of coronary disease in that group. And what we're doing is we are doing some clever math. Well, I don't want to spend a long time on this because you can go nuts. And we're gonna do a little bit more and then get rid of it. The point is that we can formalize and use rules in thinking about the conditions. So we can look at the probability of having coronary disease given these other things, but we are not making causal statements. So causation is a completely separate line of argument. So that's why the mechanistic people get mad with the mathematical manipulations, because there's no causation in the mathematical manipulation. But the statisticians never said there would be. They said that there would be a predictable relationship based on observation. The observations we make are going to be guided by what we think are causes. So, back to Mary. So Philip, you thought that Mary would have a 50% probability, but actually when I ran her through the Cleveland Clinic calculator, I got a 15% probability of coronary disease. And if you had used the ACC guideline, which uses the Diamond and Forrester model, it probably would have been closer to 30%. So, based on the 15%, we decide to get a stress test. It doesn't matter which stress test. But we'll say that the stress test we chose has a sensitivity of 90% and a specificity of 60%. So for the purposes of this exercise, whether it's a nuclear or an MRI, doesn't matter, not important. And these would be, if you're a true believer, you might have gone for 80% or something like that. But I chose these numbers because they're easy to work with and easy to do arithmetic. So, caution, just refresh our memory. Sensitivity.
So the formula?
Well, how about the idea? You can give me the formula or the idea.
Two positives were the two positive electrons mix. So, in essence, given that a test is positive, is the likelihood that it's other expenses.
The ability of the
Its ability to rule out the disease.
I'm
No,
sorry,
it's not ruled in. It's ruled out the disease. Sensitivity is the ability to rule out the disease.
That's the classic teaching, right? That sensitivity, high sensitivity is a good rule out. But, and Jeremy?
It's the probability of a positive test given that you have the disease.
Right, so if we were thinking of the probability of A given B, we would say, what is the probability, given that you have coronary artery disease, what is the probability of a positive test?
I agree.
Good. All right. So, and then specificity?
The probability of something negative given the
Right. So both sensitivity and specificity assume that you know that disease is present or absent before you proceed. So the stress test is positive. So Ryan, what should this do for how should we now think about the likelihood, I shouldn't use that word, the probability of Mary having coronary artery disease?
Felt that, given her situation, she had a 30% chance.
We were working with 15 for the purposes of this exercise, but, I mean, you could work with 30 if you wanted to, but all the other slides will use 15.
Yeah, so on our scale of 0 to 100, we're at 15. Now we have a test that was positive, so looking at our curve that goes up like this, we have new pretest probability combining what we have. A new post-test probability, which becomes our new pretest probability, which we decide to do for the test.
All of that is true, but you haven't answered the question. but that was, well done.
All right. The simple answer is it's Catholic.
That is the simple answer. We're right. The test was positive, and the test seems to have reasonable parameters. So we think that the probability is going up. How much? How much should this test make us revise our pretest probability? 6%?
The lower the pretest probability, the less your testing positive is going to affect your post-test probability. Like, only do a stress test if it's really probability to get one.
Right. Now, unfortunately, so I agree with everything you said, and that's an important point. But it turns out that the ESC will give intermediate probability of 15%, and the ACC 10%. They are not. So basically, everybody is intermediate risk in our world. So, but you are correct, and I do want to make it. I agree with the implication that stress tests have little to offer at the extremes of probability, and those arbitrary definitions from ACC aside, she's low. So we're not going to learn much. But the other part of your message is also important, and I want to emphasize it, that we can only interpret sensitivity and specificity in terms of disease prevalence when we're trying to decide how likely disease is for an individual. So let's think about this, and let's try to get be more thorough, or to be more quantified, to quantify this better. Let's step back before we do that and talk about Bayes' rule. So we've already talked about conditional probability, and we've said that the probability of Mary having a positive test, given that she has coronary disease, is the probability that Mary has a positive test times the probability that she has coronary disease divided by the probability that she'll have a positive test. So the likelihood of having a positive test is dependent on having coronary disease. And the more we think that she has coronary disease, the more she's likely to have the positive test. You know, when you put it that way, it just sounds obvious. And this is an axiom from conditional probability. So Bayes' rule is a clever variation, and I'm not going to derive Bayes' rule. If you're interested, I can send you the derivation for Bayes' rule. based on two definitions. It's not a theory. It doesn't explain anything. It is a deduction from basic axioms of conditional probability. So to adapt Bayes' rule and conditional probability to clinical work, or scientific work, we simply say, instead of A given B, we'll now say the probability of the hypothesis given the evidence. So the hypothesis might be that Mary has coronary disease, and the evidence could be that she has 3 risk factors, or the evidence could be she has atypical chest pain. Or we could add the probabilities from those two, or the stress test. Now, if we're going to think about what the beauty of Bayes' rule is, that we have to think of total probability. So the total probability means that if something might happen, it might also not happen. So we might say that the hypothesis might be true, or the hypothesis might be false, and we might look at the false hypothesis. We might look at the lack of truth of that hypothesis as a second hypothesis. So if we look at the probability of something happening or something not happening, and we add them, then we have the total probability. So it might rain tomorrow, but it might not rain tomorrow, and the total probability is the probability that it will rain or not rain. So when we put those together, we have Bayes' rule. So I hope this will become more obvious as we get back to our specific instance. So the probability that Mary has coronary disease, that's our hypothesis, given the positive stress test, that's our evidence, is the probability that Mary has coronary disease times the probability of a positive stress test given that she has coronary disease. What is that? That's our sensitivity. So that's how sensitivity and specificity tie in with conditional probability to making, not specificity, but we'll come to specificity. Ties in with conditional probability and a structured argument about whether Mary has coronary disease. Divided by the probability that Mary has coronary disease. This sounds familiar, doesn't it? Because it's a repeat. So divided by the probability that Mary has coronary disease and that she has a positive stress test, given that she has coronary disease, plus the probability that Mary does not have coronary disease, given that she has a positive stress test. In other words, what is this sentence? Specificity. So the stress test may mislead us. It's 1 minus specificity. Correct. It's 1 minus specificity. It's the false positive rate. So we can think, 1 minus specificity is the false positive rate. Sensitivity you can think of as the true positive rate. Rate of what? Rate of positive effect. So we've already answered this question. Sensitivity and specificity, these are just dreadful screens. Remind me not to hit them. Phew, that was hard. Yeah, don't touch the screen. All right, so the point is that we can relate sensitivity and specificity, or 1 minus specificity. It doesn't really matter, right? They're inverse of each other. We can relate that to the probabilities. Now, we still haven't figured out how to quantify the information we got from the stress test. So let's proceed and do that. So our pretest probability that Mary has coronary artery disease is 15%. And how did we get that? In a way, that was our first test, although in that case, we got it from the prediction rule. but you could get it from, you could get it from intuition, which is what we have to do in the office. You could get it from prevalence data, but you get it one way or the other. So that is our pre-test probability. And then the question is, what is our post-test probability in light of the positive stress test? So we've, in a way, we've covered this a little bit. If we talked about how Bayes' rule is going to tie together the post-test probability, the pre-test probability, and the results of the stress test. So to put that more simply, if we do a little bit of algebra with Bayes' rule, we can restate Bayes' rule as saying that the pre-test probability is, the post-test probability, so the probability of coronary disease, is the pre-test probability, which was the result, the likelihood, this is related to the prevalence of disease, times the sensitivity divided by 1 minus the specificity, or the true positive rate divided by the false positive rate. And this is the likelihood ratio. And that's the definition of likelihood. So you knew that, and that's great. The reason I've avoided using the word likelihood up to now is that this is a special use of the word likelihood, which was invented by Ronald Fisher. But the idea was thought of. I don't know if you invent ideas, but you thought of the idea. And it's a little troublesome because likelihood in common speech means probability. It's really a synonym. But here, it really refers specifically to the ratio of sensitivity over 1 minus specificity. And what does this do? It's a multiplier that lets us see how much that stress test, or any test, can change our opinion. That ratio is the power of the stress test to change our minds about probability. Change it from what? Well, you know, that depends on what we thought it was to begin with.
So, in the equation, how does it change whether the test is positive or negative? So, this is assuming that the test is positive, you're supposed to test size, right?
Yes, so we would have to work through a series of, shall we say, parallel mirror image equations for negative tests, a negative likelihood ratio. You can do a negative likelihood ratio. This is a positive likelihood ratio. I couldn't, to be honest, I wrote this talk Monday and Tuesday night, and there was no way I was going to get that done. So, but yes. You can kind of do the inverse of this. So for Mary, the pretest probability was 15%. And this gets back to what you were saying, that we have to have some idea of the prevalence. So pretest could mean prevalence in this case. And then we need to get the ratio of the sensitivity and specificity. Well, the sensitivity is 90% or 0.9. So in probability, 0 means something can never happen, and 1 means it must happen. And a fraction between 0 and 1 is our estimate of how likely that event is. So 0.9 divided by 0.6, and and that gives us an odds of 0.18. So let me back up. So this is a detail. This is not important. But when we look at sensitivity divided by 1 minus specificity, we end up with an odds ratio. The chances that something is, or the chance that something is not. Now that's an odds ratio. So if I'm
if I'm going to choose 2 out of, the 4 of you in this row, then the odds are 2 versus to 2. But there's a 50% probability. So the chance of them being chosen or not being chosen, that's an odds ratio. The likelihood or the probability that of being chosen out of the entire group, that's a probability. It's the chance of being chosen out of the entire group. So we end up with an odds ratio, and then whoever does that, nobody. So then we convert it back to a probability, and we have 20% when we do the arithmetic. So the positive stress test with a sensitivity of 90% and a specificity of 60%, which, by the way, is not that far from where no stress test plays, has changed our opinion about the likelihood of coronary disease from 15 to 20%. So the likelihood ratio is one way to say that we have learned from experience. The experience is observing the results of the stress test.
I think, point 9 divided by 0.9 divided by 0.4.
It should be.
33%.
I made a mistake. Yeah. Thank you.
I wouldn't remember.
No.
It's 1 minus, yes. It's specificity with 60. So
yeah, you're right. So I'll fix that the next time around.
40%.
Yeah. So the post-test odds are 40%. Okay. Yeah, so 40%. So actually that's quite a bit. So from 15 to 40%, but it hasn't brought us certainty. So there's a big change, but we may or may not decide that that's clinically helpful.
So you're saying we should get stress MRIs
Yeah, I don't know. You know, it wouldn't change that much. Yeah. So if you have someone, as a rule to remember, if you have somebody at the extreme, then the stress test might get you into the middle range, but it won't get you into the high end of the range. All right, so now Mary asks about her stress test. And we say that it showed inferior hypokinesis. Then we remember, that's not right. It showed anterior dyskinesis and inferior akinesis. Mary asks, well, so what? They're both abnormal. Would it make any difference in the probability of disease if the result was one or the other? So, do you think it would? How so?
Well, that's on the that's the that's abnormal. There is a chance that it's a false positive, or less severe, but if it's more severe form, chance that the test is positive, and actually shows disease is also higher, so that should increase your post as well. It's going to be more. So
can you put that in terms of sensitivity and specificity?
That's well,
you can.
so okay, so the chance that it's a false positive is more. So that means it's more specific. It's more.
Which one is more?
The one with more disease or more abnormality.
Okay, but we want to think about total probability. So which one is more sensitive?
The first one would be more sensitive.
So inferior hypokinesis would be more sensitive, but would have a lower specificity and a higher false positive. And multiple areas of akinesis would have a high specificity. There'd be fewer false positives, but it would be less sensitive. So we could express that in likelihood ratios, and I've just arbitrarily chosen a sensitivity of 0.95 and a false positive rate of, this should really be 1.2. I'm sorry, 0.2. And likewise for anterior dyskinesis and inferior akinesis, the sensitivity is lower. I wish I'd stopped doing that. But the specificity is higher. So the point of this exercise is that most diagnostic tests can be interpreted at different thresholds for the disease. And the threshold you choose will determine the sensitivity and specificity you observe. So it's in a way, it is a simplification to say a positive stress test, a positive VQ scan, a positive whatever it is. I mean, if you can think of any test where really there is a division that is always for all patients clear cut, as opposed to gradations in different groups, and gradations according to how severe it is. A BNP of 450 as opposed to 4,000. So how are we going to cope with this problem about multiple thresholds of the test? So we're going to use the receiver operating curve and the C statistics. So you knew this was the last part of the lecture. So why is it called the receiver operating curve? Radar. In World War II, radar operators received blips on the screen, and they had to figure out if it was noise or an enemy aircraft. And they needed some criteria by which to notify the defense forces that incoming airplanes were arriving.
So this was after Pearl Harbor, I'm assuming?
I don't know. Now, the likelihood ratio is very much linked to the receiver operating curve. The receiver operating curve gives us a series of likelihood ratios over the span of all imaginable sensitivities and specificities. By the way, all imaginable means 0 to 100, because 0, it can never happen. 100, it must happen. 100 is nirvana. 0 and 100 are nirvana. We are certain. We are God. Everything else in between is human. We know that. But we can estimate the chances. So on the x-axis, we have 1 minus specificity. On the y-axis, we have sensitivity. Or you can think of it as the true positive rate divided by the false positive rate. So a test in which the true positive rate and the false positive rate ratio is 1 would be a straight line connecting 0 and 1. So that would be a test with an area under the curve. If we look at the area of this rectangle, it's not a curve, the area under the straight line would be 0.5 of the whole. That test would be as good as flipping a coin, and if we could figure out how to build for that, that would be really cool. But most tests will have a curve And here I put a star and the numbers 40 and 83. So 20, 40, 60, 80. I didn't touch the screen this time. And then 20, 40, 60, 80, and it's a little bit higher. So how would you put into words what 40 and 83 mean? One minus the specificity, so 1 minus 60 is 40. So we're looking at a false, the specificity of the test was 60%, the false positive rate was 40%. And then the 83, sensitivity. So these are matched pairs. Each point is a matched pair of sensitivity and 1 minus the specificity. So this answers the question, how are we going to judge the sensitivity and specificity of a diagnostic test when we can interpret the diagnostic test in multiple different ways with different sensitivities and specificities? This will pair the sensitivities and specificities. It also shows us the trade-off. We can be more sensitive, we can be more specific. Which is more important? Sensitivity or specificity?
Depends on for a patient or a lawyer.
Yeah, it depends whether you're more worried about missing disease or more worried about falsely labeling. There is no right answer. Usually we'll choose something in the middle somewhere. Now, one other question about this. When was the last time you ordered a test with a known sensitivity of 10% or a known specificity of 10%? Where did they get that information from to draw this curve? This curve obviously is made up. It's extrapolated. Yeah, there is no such information. So most of the curve is actually not derived from observation, but from matching a probability curve to a restricted area of sensitivity and specificity.
Mostly the 0.5 to 0.8 range or behind with the majority of our specificity and sensitivity, so that's kind of where we just extrapolate.
Yeah, and I have to admit I'm not an expert on this. So now, we talked about how sensitivity and specificity vary with the threshold of the diagnostic test. But sensitivity and specificity are also going to be affected by the standard we compare it to. So here, a calcium score was compared to a 50% stenosis on invasive angiography and a 70% stenosis. And the area under the curve is not surprisingly larger. 0.75 doesn't sound like it's a lot bigger than 0.7, but it's very hard to make these. The area under the curve is not very sensitive for these distinctions. So a difference of 0.5 would make the authors ecstatic with happiness or some other things, depending on what they're doing. The area under the curve is a one number summary of how good the test is. So if you look at all the combinations of sensitivity and 1 minus specificity to summarize the accuracy of all those different calculations, we look at the area under the curve. And the higher the area, the closer the curve is to the left upper corner, the better the test. And the area under the curve is also called the C statistic, and C stands for concordance. Concordance with what? It's because the area under the curve and the receiver operating curve has been used to look at the goodness of fit of models, then the concordance is between the model and the observed status. So C statistic is really just a synonym for the area under the curve. All right. Mary learns that her stress test was positive. We already covered that, right? We told her that. We sort of forgot whether it was hypokinesis or anterior kinesis. We said, Mary, cut it. And that the area under the curve for her stress test was 59%. And I just pulled this from an article which happened to be looking at ischemia in the right coronary artery territory, but it doesn't matter. It could be 60%, could be 70%. She asks what that means for her in plain American English, not English. How do we explain that 59% number to her in terms of her chance for disease? Does this have any meaning? Or what does the 59% mean? So the area under the curve is 59%. It's a measure of the overall accuracy of the diagnostic test we ordered. Yeah, well, it's a disappointing result.
It's low, it's very low, but it means that this test will capture 59% individuals who have true disease. We have more than we have years.
No, I think it just means that the 9% of it basically tells you about the accuracy. So there is a 59% of chance that whatever the test says is true.
That's why
I know it's the C statistic. Yeah, we're still on C. We haven't gotten to D or any of the other more advanced levels.
No, the Z score, oh my God. No, I don't think we can that, because the Z statistic is 0.5, and
0.59. But 0.7. It doesn't matter.
so this perfect.
But just put the meaning of it into words.
Any words that have this test times and then
when 6 out of 10 have disease, but having this is possible.
Say that one more time, Shadi. I get confused too. No, seriously. I mean, these probability statements, the conditional probability. So if she has a positive test, or if she has
the disease,
then that's correct.
when capture.
That's exactly what it is. So it's a restate. It's much closer to sensitivity. We really can't say anything about Mary's probability of having disease. We didn't have the area under the curve had nothing to do with that. Just the sensitivity and specificity have nothing to do with that, without knowing the prevalence. So of people, if Mary has coronary disease, there is a 59% chance that she will be correctly classified as high risk with a positive test. That's the meaning of the area under the curve. It's a classification. It's a discrimination. So what is discrimination versus, I'm getting ahead of my slides. This is terrible, ahead of my slides.
what happens if she has a test twice?
Well, that has to do with reproducibility. You can actually use Bayes' rule for a series of probabilities and calculate what the probability is. So you would actually change the probability. And if you repeated the test several times, it's not that the test is useless. You would just have to calculate what the probability would be after those variations. Yeah.
Yeah, can you verbally say the difference between?
So, sure, because they're similar. So sensitivity is of people with disease, or given that you have the disease, what is the likelihood that you will have, what is the probability that you'll have an abnormal effect? The C statistic we'll get into. So it's going to be that plus something else. because the C statistic is sensitivity divided by 1 minus specificity. So hold that thought about sensitivity, and we will elaborate its difference with the C statistic in words in a moment. So what do we need? We may have answered this question. What do we need to add to the area under the curve to get to Mary's probability of disease? So you have 3 choices here. So the prevalence of disease in the population to which Mary belongs, would that work? The probability or the pretest probability or odds of coronary disease before the test was performed, or the predictive accuracy of the test. Actually, they're restatements of the same thing. Yep. So if one is correct, 2 must be correct. What about 3? What is 3? Who could put predictive accuracy into words? Yes, probably. Okay, probably predictive value.
The probability that the test will be positive if actually if the test is positive, maybe you study.
What is the probability that she has coronary disease given that she has a positive test? So that's the question we ask in the office. We don't know if Mary has coronary disease when she comes to pre-operative. We may know her insurance status, but we don't know if she has coronary artery disease. So the predictive accuracy is affected by prevalence. So these are all 3 linked. The predictive accuracy is influenced by prevalence. So it's in here, but indirectly. These 2 statements deal directly with pretest probability, which we take to be prevalence in that population. So prevalence is not quite the same thing as pretest probability. We are using it as our pretest probability. I still haven't forgotten about your question. And if we don't get to it in the next 2 slides, then I'll come back to it. I think it's in there. So let's talk about some problems with the receiver operating curve. We already talked about one issue, which is that the receiver operating curves will look different depending on the standard of truth that you use to judge your diagnostic test on. So you can change what appears to be the sensitivity and specificity by using a fractional flow reserve of 0.75 or 0.8, or in our lab, 0.83. Now, let's talk about another problem. We already mentioned that the extremes of the curve are sort of made up. They're not made up, they're extrapolated, which to me is the same thing since I can't be arithmetic. Here, the authors of a paper highlighted the area under the curve between a sensitivity of 70 and 80%. But the curves are different shapes. So there's no rule that says all diagnostic tests have to have the same ratio of sensitivity to specificity at a given sensitivity. Which of these diagnostic tests, which have the same area under the curve, close enough, 0.11, 0.12, don't. So the goodness of fit, the goodness of the test overall from 0 to 100 is the same. But in the range of 70 to 80% sensitivity, and are we ever really going to be interested in a test with a sensitivity less than 70%? We're getting perilously close to tossing a coin. We have a much different result. So which of these would you prefer? Well, no, because the sensitivity is the same. Both have a sensitivity, both have, this sensitivity is the same as this sensitivity. So your chances of missing disease are the same. So this one, so the false positive rate here is 20%. The false positive rate here is 50%. So it doesn't matter to us that the area under the curve is the same, because in the region of the receiver operating curve where we are interested in testing patients, one test has much better characteristics than the other. So the C statistic is a very gross statistic, and by itself may not be a good guide to the clinical utility of a test. Now, why don't we simply report C statistics, partial C statistics between 30 and 70. By the way, that's the usual range I'm sorry, that's not what I meant to say. Between, say, 70 and 90 sensitivity. Why don't we simply restrict our C statistic? And the answer is that when people have tried to do this, the receiver operating curve for two tests tends to be extremely variable, and slight changes in the definition of what constitutes a positive test can result in reversing of the order of which test is better. So probably we're dealing with small numbers and a small range and getting too much variability.
How many calculators you can get under the curve? Is it just the area that you're highlighting?
It's in the dark gray.
Only the dark
Yeah.
area?
Yeah. So we're talking about the area under the curve, but just between 70 and 80%. So it's between these two dotted lines. So, right. So the box is the same. The problem is the size of this rectangle is the same. It's almost a rectangle, whatever that is.
Got it.
But this rectangle is shifted over into a more desirable position. All right, thank you. So somehow I got this wrong. So your question was, how does sensitivity differ from the area of the C statistic? And the answer is that the C statistic is more complete. So the sensitivity asks, given that you have disease, what is the probability that you have a positive test? And the C statistic will add to that, given that you have disease, what is the chance of a false positive test? And it wraps that into one number. So I'm going to end the lecture here, and I have some summary slides if you want them, or we can skip them. But I do want to, before I end, I do want to say that I'm focused on receiver operating curves and likelihood ratios for diagnostic tests. But they are also used for prediction rules and to judge the adequacy of prediction rules and for other prognostic reasons. And there are many problems with the receiver operating curve in that area too, but that would be a whole nother lecture. So rather than summarizing, or going through the summary slides, and you can get them all from Elizabeth, I would say that what I tried to do is show you how conditional probability and Bayes' rule, in an intuitive sense, can help us learn from experience by showing us how we can update our probability given new information. And then to deal with the problem of the variability and how we interpret our tests, we can use a receiver operating curve, although we have to be careful when we do that because of the pitfalls of the receiver operating curve. And we should know what the value of the receiver operating curve answer is in the range of the sensitivity we're interested in, rather than relying on the p-statistic as the only measure of whether it's reliable.
Oh, good, I don't even have to clean up.
How long did it take you to wrap your head around the?
Oh, one time I missed that arithmetic.
I didn't call you on that.
That was great.
I calculated.
No, I didn't recognize you. I didn't make that.
More likely to get.
I'm sorry, but I